Dobré dopoledne. Good morning, ladies and gentlemen. It's my honor to introduce to you another speaker this morning, Professor David C. Webb. Professor Webb is Associate Professor of the STEM Education at the University of Colorado, Boulder.
Yeah.
He is also a renowned expert in mathematics teaching and learning in mathematics education. He is involved in several projects, national in the United States and also international, that deal with innovation of teaching of mathematics. He is leading world expert in this field. He is also Associate Director of Freudenthal Institute of the United States. Yep. And beside this, he is proud father of 4 sons. And he is very good companion for every event and discussion. So enjoy him. David.
Thank you. And well, first, I'm grateful to be here, to be invited to speak here. This is a wonderful conference, and so the invitation is welcomed, and I hope I can give you a glimpse of some things in the future, and some things that have challenged us in the past related to the topic of computational thinking. So as Roman had mentioned, I am math education faculty at the University of Colorado, and you might be wondering why Pac-Man, why this formula, why a jaguar, a predator chasing after something. Well, actually kind of all related. And so we'll get into it a bit in the presentation. The focus of the talk is on computational thinking, which even just by the name already sounds like mathematics, computational thinking. However, computational thinking has its origins in computer science, and more recently has been taken up by science educators, interestingly, and has become a goal for STEM education, including math education, and math education has been kind of late to the game a little bit here, which I'll get into in this presentation. So I'll just give you a little personal background first, and the rationale for this talk. The heart of this talk is what is computational thinking, and I'll give many examples of how you might consider this within math education. I'll also discuss some historical and recent attempts to integrate computational thinking in math education, and one thing to consider coming away from this is, what is it? What is this computational thinking you're talking about? I'm not sure if you've heard about it. Maybe you have. Maybe it's been in conversations here in the Czech Republic. But my goal is to come away with a better understanding of how we as math educators might take this on as a construct, as a topic for the future of math education. So some questions to consider here. First, understanding these principles. What are ways this has been taken up after we figure out what this is? And what are some known possibilities and intersections? The goal here, though, is the opportunity that I see as computational thinking could provide opportunities for more innovative, authentic, student-centered instruction to make sure that mathematics is more engaging, more relevant, and that's the idea here, to see what's possible. So, before I was faculty at the University of Colorado, I was a lower secondary and upper secondary teacher in Los Angeles, in California, Southern California, and but even before that, before I was a teacher, as an undergraduate at University of California, Los Angeles, at UCLA, I was a math major there. For a brief little time, I was also a computer science major before I became a math major, so I had experience in both. And I was already using computers in courses as an undergraduate in numerical analysis, and one of the courses in particular, as a math major, was this course where we were looking at the mathematics of computer animation. So if you know about animation and you know about the mathematics of computer animation, this won't be any surprise to you for those that don't know. And when I took this course, so this was back in 1987. You think about, this is before the internet was very public. This is at a different time of use of computers, but we still use computers. And so in 1987, I found out as part of this course when I was a senior in my last year as an undergraduate, I found that, oh, well, there's actually a purpose to linear algebra. And at the end of the course, we were doing projects where we would animate objects, and it was more than the kind of stick figures you see here on the screen. But the nice thing about the linear algebra is how things like translation and rotation, and if you wanted to work in 2 dimensions or 3 dimensions, how that would play out on a screen, how you would take points, and using linear algebra, how you would move these things around the screen. I just began to wonder, why did it take until the end of my undergraduate experience to figure out the purpose of linear algebra beyond eigenvalues and all these other things we were trying to figure out? So that stayed with me for a while. And I got more involved later on in projects like the Scalable Game Design Project. So as faculty at University of Colorado, I interacted and collaborated with some computer science faculty, and the goal of this was to get computer science education into lower secondary classrooms. So students would program games. They would code games. So lower secondary students would do this. We initially had the idea of, well, 30 teachers, maybe 1,000 students involved. By the end, we had 500 teachers and 50,000 students involved. It blew up. It became, everyone was talking about it. It was in many states in the United States and some other countries as well. But the other piece is around the same time, around 2008, when this project was starting, there were already discussions in the United States around computational thinking, and an argument for paying more attention to this and having this be part of students' experience with STEM. The other thing I was involved in 2018, right before the pandemic, was I'm a math educator, and I was invited to be part of the Colorado State Standards to develop computer science education. So I got a chance to see what was happening in computer science and policy that was going out to teachers and how that might change things. At the time, the state of Colorado had the legislature, the politicians made a decision to require high schools to offer computer science courses. So it ended up in politics as well. You might wonder, why are politicians getting involved in education in this way to require more computer? It should just be something that's offered. Well, that wasn't necessarily the case. Going back 40 years in the United States, one of the reports that came out complaining about the state of education, in particular math and science education, was this report called Nation at Risk. It was in 1983, and there was mention there of computers as one example of how the world has moved on ahead of science and math education. So they're already setting these markers down. And that was 1983. Again, think about where computer technology was 40 years ago. It's a much different place, right? Personal computers were just starting to become popular, just starting to be used in schools. In this report, they also argued for more mathematics education. Before this report, in the United States, 2 years of math was required. After this report, 3 years of math, 3 years of science, and they asked for 1 semester of computer science for graduation from secondary. Now, what's interesting is the 3 years of math and the 3 years of science, those were implemented right away. The half year of computer science, that went on for decades before that ever got implemented. It was always just kind of left behind. Code.org, so this is only about 5 years ago. Code.org has done a lot of work in the United States to bring attention to computer science education as a topic of study and to prepare students. So at that time, they identified 36 of the 50 states, including the District of Columbia, now allow computer science. Now here's the real interesting piece, and the message to convey here is they use computer science now to satisfy high school graduation requirements for math or science. That it's basically replacing some of the required math courses or some of the required science courses. It's not saying that computer science is required for high school graduation. It's now computer science is making room for itself. That was in 2018. I just looked up the report earlier this week because there's basically a table associated with this, an Excel file. I looked up the Excel file. Now it's all 50 states. All 50 states have this policy. So policy is already moving to favor computer science education. So it leads to the question, what to do as math educators about this? When I was an undergraduate, computer science was taught in the math department at the university. It has its natural home in mathematics. So what's become of late? Who's going to teach these courses that are now being offered at high schools? Well, it's probably going to be some of us. Oftentimes, those that end up teaching the computer science courses are math teachers with some interest or some computer science training, or, well, somebody has to teach this and you know math. So it's what's happened in the United States. It continues to happen. I'm not sure what's happening here in the Czech Republic on this, but this might look a little familiar to you. This also came up a little about 8 years ago. This was a survey about which subjects do students like a lot. These are US students. It's kind of interesting because, you know, it's not surprising that art and design, performing arts would be near the top. These are courses they like a lot. What's really surprising is how computer science and engineering, it comes up pretty well. Mathematics, not so well. So, and I don't think it's just the United States, right? This is, you know, the ones that like it a lot. If you asked, do you like math? Is math interesting? You might get higher numbers here, but this is like 5 out of 5 on a survey, right? So that's interesting too. So I do think computer science creates some opportunities. There's also some if you really have no interest in doing coding or programming in math education, not to worry. There's many opportunities to engage in computational thinking without getting into computer science. But I want to start there because that's where some of the discussions happen. And there were some things I learned about computational thinking from these experiences. So what is computational thinking? In the United States in about 2006, Jeanette Wing, who at the time was at the National Science Foundation, made a proposal for more computational thinking in schools. And so I just want you to look at some of the verbs and some of the actions described here. It's about thinking recursively, using abstraction, decomposition, modeling, problem solving. Sounds kind of familiar. Sounds like mathematics. Now, when this definition came out, it was so vague that people started thinking, well, anything could be this. If I'm baking a cake, Is that computational thinking? So there was a debate at the time back and forth over what computational thinking really is. So the ISTE, or ISTE, International Society for Technology and Education, they gathered a number of educators together and got more clarity on how they were going to define computational thinking. And this became used more often across the United States as, well, this is what computational thinking is. Now, again, if you look over the verbs and the actions here, you will see this looks remarkably familiar. You could see how this might end up in a computer science course. Strange thing is, it looks like mathematics. Formulating problems, representing data, algorithmic thinking. So it's about the reasoning that occurs. So this is how in the United States many will refer to computational thinking as it's defined. Just a quick show of hands. How many of you are familiar with the phrase computational thinking here in the Czech Republic? Just, has this come up at all? Show of hands. Anyone have? Okay, a few of you. Okay, it's coming. It's on the way. So hopefully I can give you some, again, a peek at the future for what's coming, because at some point in 2023 and beyond, who is going to teach and use computational thinking for future generations of students? We're going to have some say and responsibility in this, most likely. So here's also from the same report. Computational thinking is enhanced by confidence in dealing with complexity, persistence with difficult problems, tolerance for ambiguity, sounds like problem solving, deal with open-ended problems, and to communicate and work with others to achieve a common goal or solution. You could see how this could happen very easily within the context of math, and not so much even, because sometimes a computer science class can avoid these things. It can just be, here, code this, does it work? Compile it, does it work? Because computer science can be taught in a very rote way as well. But these aspects, which we've been calling for in math education for some time, again, that's part of how computational thinking is described. Here's from the math standards in the United States, the reasoning goals that have been described, so-called standards for mathematical practice. Again, it's just a few turns of phrase, a few shifts in words, but again, it looks remarkably familiar. Okay, so a lot of text to process. Here's where I want to go with this. So this is basically how computational thinking has been defined by, these are the ways to enhance it. These are the ways, this is how it's being defined. These are how you know it when you see it. So this is a recent article, I think it was just published maybe a month ago, from science educators. So science educators have been looking at computational thinking in the United States. They go back to Seymour Papert, who originated the phrase, and he talks about it as a cognitive process, and then mentions a viable definition of computational thinking must center on what's going on in your head. It's about thinking. It's about thinking. So they identify this, Hurt and colleagues. Computational thinking is the cognitive processes involved in building or modifying a mental model of these tools' functionality. We just try to make that a little bit more accessible. When you think about the various tools, and the various tools presented at this conference, from sketchometry to GeoGebra and a whole host of other things, one thing to think about related to computational thinking is, what can this app, software, or whatever this tool is, do to help me solve this problem? That's about computational thinking. It's recognizing the power of technology and technological tools to do the abstraction, to do the algorithmic thinking. If everything that we do in math education pretends that computers and other forms of technology don't exist, math is going to become less and less authentic, relevant. Students are living in one world outside the classroom, and we're teaching them about a different world of mathematics in the discipline and some very important goals inside the classroom. So I want you to just think about this for a moment. And I want to invite you to think and pair and share with somebody next to you. Have a conversation. What are computational tools that you use in day-to-day activities? What are the computational tools that you use to help you solve problems? What's the technologies you use? All right, and then give you about 2 minutes for this. I want you to think about what your students are using. All right, give you about 2 minutes. Have a conversation with somebody next to you. Say hello, and talk about these 2 questions with somebody next to you. About 1 more minute. 1 more minute. Okay. All right. I'd like to, well, I might not be able to understand you if you speak in Czech, but, but somebody else can probably translate for me. I just want to get some ideas that you talked about already. What were some things, let's start with the first one. Computational tools that you use in day-to-day activities. What did you come up with? Any ideas?
Mobile phones.
Mobile phones. Yeah, I mean, these are everywhere. Yeah. We use these. What about students? yeah. Okay, other ideas? What's that? Oh, tablets, yes, yeah. We just saw that in the last session, right? What else? Laptops, okay, so laptops, tablets, phones, which?
Brain.
Oh, the brain, well, that is a very powerful technology, very important one. None of this happens without your brain, right? Yeah, the watch. The watch. There's measurement data being collected all the time on some of these watches, on smart watches. So that's just some examples. I figured you might do this. For students, I mean, they're using things like TikTok. Now you might think, well, that's not computational thinking. That's just videos and performing arts and likes and dislikes. Well, they're editing videos. They're using all sorts of tools to get things just right. They're zooming in, zooming out perspective. There's lots of interesting things going on that they just do because they want to do it. They don't think about it. Instagram, same kind of thing. So the social media software is leading students to do certain things. to get things just right. For some, it could be lucrative. For some, they could get lots of shares and likes. Yeah, so these social media platforms, you know, Meta, Facebook, YouTube, WhatsApp, Instagram, Messenger, and so forth. So these are quite popular. This is a recent survey. I should have put the information down here. You mentioned laptops. Yeah, we had a whole bunch of work on this already and more to continue. But software that's used outside of schools, things like Google Sheets or spreadsheets, it's a very powerful tool. Who teaches that? Do students use it in an authentic way? Because when they get out of school, they'll most likely be using that at some point. But even these other tools that get us to help think about abstraction and representation and problem solving. Oh yeah, this one's come up recently. You can already hear about the math that's coming up here. Get geometry, right? We were at a VR lab yesterday. How can VR be used as a computational thinking tool, virtual reality? So yeah, the phones, that's interesting. They have so many measurement tools on them to allow us to engage in mathematical ideas, but we often don't use them very much. And yet, we all seem to have them, or most of us have them. So these are computational thinking tools. And when you think about, okay, if I need to solve this problem, how does this computational tool help me? That's a starting point for thinking about, okay, here's a place to start integrating some of these ideas and taking what students are bringing to the classroom with their experiences and their expertise and bringing that into some projects or lessons or things like that, or just exploration. What's happening here? Okay. Back to computer science for a moment. So in the Scalable Game Design Project, we went around to various schools. This one happened to be in Missouri, in the middle of the country, United States. And we just went around with a camera and we're asking students, you know, what are you doing? What are you learning? And things like that. So I have a few videos here that I want you to just kind of listen to. I think there's some English subtitles below, so we'll see how this goes. But hopefully you can kind of get the point of what the student's trying to say.
You have to always work through things because programming games take just a short time. You need to always work through it. So I learned about perseverance and a lot of thinking and common sense. Because if you don't know like common sense and things, it won't help you in this class because you need to put certain things together because you can't always get help, so you don't have to learn to put things together.
You do a lot of this on your own. You have to figure out things on your own.
And so he may help us once in a while, but he makes that like what we're doing now.
So perseverance, problem solving. The interesting thing about computer science and coding and programming is troubleshooting. You're going to make mistakes. It's accepted. You will make mistakes. And part of the process is to debug, figure out those mistakes, and continue to improve over and over and over again. Now, mathematicians do that too. A proof just does not come like a bolt of lightning and you've got it and it's all written down. There's a lot of thinking and iterative problem solving and community collaboration and trying to make sense of, is this valid? Does this work? Why isn't troubleshooting and allowing mistakes to happen and embracing how to fix those and address those and allowing space to go back even part of math education? But it's just a given in computer science. So that's one student. I've got another one coming up in a moment. But I want to show you this. So this is one of the games students would program. They could change the pellets. You're all familiar with this, Pac-Man? Okay. So pellets, these are the power pellets. So some of you might know that you're going around picking up the pellets, you're gaining score, and then, well, we can just actually look at it. So let's go here. Well, there it is. So What you see below here, and I'll zoom in just so you can see this. One of the goals here is, as you're going around the board with Pac-Man, you got to find a way to make the ghosts chase you. So how do you get the ghosts to chase you as you're moving around the board? Actually, mathematics. What happens here is, let's see if I can get this to zoom in a little bit. Well, I'll zoom in a little more. Let's see. So basically, Pac-Man is going to distribute a cent. And it's going to take, so this is basically the point you're at. And it's going to take the point above it, below it, to the left, and to the right. Add those together and either multiply by 0.25 or divide by 4. Basically going to take the average value of everything around you. And it's going to do this very fast. And it's going to create this hill where the Pac-Man is the peak of the hill. And then the ghosts just look around. What's the greatest value? And I'm going to go to the greatest value. It's all mathematics. So let's go back here. This is going to be what one of the students said about even programming the game, if I have this correctly. Hang on.
And tell me what you like best about your time. I like how it wasn't easy to design. It took a lot of time and effort, and it just was complicated. In what way do you use design? Do you mean build the rules, or create the world, lay out the world? Like to get the ghost attack, that was kind of the hardest part for me, but I think it's the most fun part because normally this kind of stuff comes easy to me, but it was just fun because it was kind of complicated.
So lower secondary student, programming Pac-Man. It's not that it's too hard. That's the part she really likes. She likes the complicated part, and getting it to work is an accomplishment. The funny thing is, the formula for this, and this was brought up at the beginning, to get the ghost to chase Pac-Man is called collaborative diffusion, and we can get very formal about this. This is basically you're going to sum up the values, take those differences, and then you can even have some kind of factor that's rolled into this. We're not going to teach this with middle school, lower secondary students. It's going to look like this. So we get to actually the heart of what this is all about. And let's see. Oh, I lost my cursor. You can see as Pac-Man is moving around the board, this is what's happening to the values of all of the cells around Pac-Man. And now the ghost can figure out how to change Pac-Man. So it's one thing to show a visual. It's another thing to show a formula. But what we show the students is basically, okay, this is you. Now, if you're this cell right here, you're going to take 1,000 and 0 and 0 and 0, divide that by 4. So the value you're going to get here is this one. But then you're going to do it again, and again, and again, and very fast. And next thing you know, you have this hill to climb. So that's just the beginning. That's just scratching the surface of the many things with game design. This can be used in predator-prey models, where a cheetah's chasing coyotes or what have you. But there's also some ways these tools, these computational tools, can generate mathematical data for us, like the predator-prey model. Like you've got fish here. And the fish are, let's say the red fish are going after the yellow fish. And so for this one, I need to do this. This one, let's see. I need to back up. All right. So you see the fish here, and basically the red fish have code behind it in terms of When you're close, there's a % chance you're going to eat the yellow fish. How the red fish are moving, it could be random or it could be very directed. You keep track of these things, you keep track of the totals. But as a simulation of a predator-prey model, it looks something like this. I'm going to slow this down, otherwise it's going to be really hard to see. But so you see the red fish on the graph, the small fish, the yellow fish here. And you kind of see the yellow fish are reproducing. So are the red fish. But then the red fish, when they get close to the yellow fish, start eating them. And then you get a model that starts looking like this. If I speed this up a little more, you can kind of see how these graphs work. And eventually, that population of yellowfish starts coming back down a little bit. And so you get to these cycles. You can actually just press export. It puts to an Excel file, and you can look at the data in terms of cycles and graphs. Computational tools like this or Scratch and others can generate data where students can actually change the probabilities and see how population cycles kind of grow and increase and change over time. But it puts them in a situation where, well, it looks like it might crash. Those yellowfish are, I don't know. All right, we'll stop there. You get the idea. These computational tools can generate data. There's simulations that can do some nice math work for us, but students get into percentages and probabilities and basically the mathematics behind how these things work. So there's also some other computational thinking patterns. So I looked at collaborative diffusion. You can decide how often to generate new fish. When you collide or touch each other, you have to sense that you're next to each other. What's the chance that you get eaten or that you get sick or that you don't get sick? Absorb, same kind of thing. So anytime you're generating a model, you're going to be dealing with percentages and formulas and equations, and it's going to be in the context of computer programming, but you're going to be making sense of math content in a different way. You're going to be building and seeing patterns. You'll see how repetition changes values and the cycles, because you're going to be doing loops over and over again, maybe. It may relate to geometry and where you are on a board and how to know where you are on a board to do something. So you got to have the coordinate system and know how to identify. So you can kind of see, to model games, it's like modeling the world. It's not a very big difference between game design and science simulation design, or even just math design. Some very explicit content with mathematics, understanding variables, and you get strange stuff in computer science. We have things like x equals x plus 1. Wouldn't talk about that as so much of an equation because it doesn't make sense. How does x equal x plus 1? But when you're talking about recursion and how to make sure you're doing recursion in a computer science program, where are students going to learn that? Because when they're getting out and maybe getting jobs involving computer coding, or even not, maybe they're using R and statistical packages. Where are they going to learn this stuff? Math can be a really interesting context to look at. Here's what we're doing in math, where we're balancing equations, but here's what you're going to do when you see equations in this computational tool. Here's how they're similar. Here's how they're different. Inequalities and equalities, randomness. How do you make something look random? All sorts of things in programming and mathematics that can be looked at here. All right. So math education in the United States just took up these ideas, and now we fully integrated computational thinking and math education. Nope. No. They've done it. The science education community has done it. So what they've done, if you look at the next generation science standards in the United States, they talk about computational thinking. You will not find computational thinking anywhere in the math standards in the United States. They talk about simulations, they talk about modeling, they talk about technology. They talk about it as if we're in 2023. You look at the math standards, you'd be hard-pressed to find technology in the United States. You wouldn't find computational thinking mentioned at all, yet. It's coming. And more math educators are getting involved. We're probably going to have our next release of national standards probably in the next 5 years. But science educators are doing this. Look, this is an example from the same article from 2023 where they're giving an example of how computational thinking plays out in science education. They use a graphing calculator. This is how we're going to use this tool to model bacterial growth. So it's being taken up by some educators. What's our responsibility as math educators to take on computational thinking? You could do it through computer science and having some of those as projects in classes. There's also other ways to do this. There's some other tools I want to show you. You've seen some this week. One of the problems we're trying to address is this, to make math more relevant and authentic. Maybe we can change the nature of this. So, yeah, this is kind of the mindset that we want to develop among students. This is about strategic competence. This is about how to know what the best tool is to use this. And so are these conversations we're going to start having with students? Are these the kinds of things we're going to look at? And this is something we can even ask ourselves as educators. How do you use this as an educator? Where would you find value in this? So it's about formulating problems, algorithmic thinking, representing data, generalizing and transfer. So I'm going to show you just a couple things. I think I have a little time left that has been developed by PhET. I don't know if you've heard of PhET before. If we had probably science educators in the audience, you might have heard of PhET. PhET is actually physics education. It was developed by a Nobel Prize laureate, Carl Wyman at the University of Colorado Boulder. They started with physics applets and simulations, and now they've moved a great deal into math applets and simulations. Here's just one example that came out last month. This one's related to quadrilaterals. So let me just show you something here. I'll put that back up if you're trying to get that QR code. But I just want to show you what this looks like. And you basically can move this around, and you can show the name of the shape, and you can try to identify what's happening here with these different shapes. So basically, it's just investigating quadrilaterals. And when does something change from a trapezoid to a square? This is upper primary, lower secondary, and just trying to investigate different patterns. The other thing with PhET is you can go to translations, and you can get a translated version in Czech that looks, and this is for all of their simulations. So if you want to do science ones as well. So you can actually go and download the Czech language version and see something similar here. Is it a triangle? I didn't know some of these shapes. Basically, you can kind of see, this is just to explore what are ways to help students abstract what is and isn't, how to identify quadrilaterals. It's something we do as part of content. And then it's like a sandbox. They just get to play with it and investigate. You can also add in diagonals. Kind of like you were showing earlier with sketchometry, right? You can also look at the angles. Now, this is just, it's a very kind of tight, focused type of application. So, but that's just one example. If you go to the PhET website, let me just go here instead. Hopefully the internet's still working. slow. Ah, I was afraid of that. Okay, so I do want to show you one more of these. So again, how can this tool help me reason, abstract, figure things out related to, in this case, something very, very focused? There's at least, I don't know, I'd say close to 20 math applets on PhET. They're free. You can see they've got the translations there. But there's another one that was also developed recently. So we were doing this for a project, and they wanted something involving statistics and center and variability. So you can go to the PhET, colorado.edu, search for center. You'll find this. I'll show you an example of how this could be used in just a moment. But the idea here is, okay, so how can this computational tool help me solve problems? How can it help me figure out ways to tell the difference between this type of data representation and this type of data representation? So again, from almost like put my teacher hat on, that's how I'm going through this. And what's the type of reasoning I'm going to be looking for when it comes to the students in class and the kinds of questions I'm going to ask? So most of these PhET simulations have a kind of a play area, like a sandbox, just to investigate. And then you also have some directed activities as well. So I'll go back to this one. This one should be up and running, hopefully. Yeah. So with this, you can just look at, and they've got multiple screens here. They've got mean and median here. They've got variability here. But basically, you're just kicking a soccer ball. There should be 15 there eventually. All right. So basically, I have a representation of data. Again, a tool that's going to generate some data. And what you can do with this is just focused on the median at this point, right? Just says median here. So I can predict where the median is just by sliding this. Maybe here. And there's other things I can do with this in terms of just checking where the median is after predicting. You can show, like, how did you figure that out in terms of it'll sort data for you. And the other thing you can do with this is once you've identified where the median is, what are the different effects I can have when data changes? So what happens when, is it going to change anything with the median if I bring this point along? Put that back. No, that's not how the median works. Unless no, right now it's even. But if I go to something like this one, and now I can compare the mean and median. I can also reorganize the data if I didn't like the way this data turned out. I can just put some more here. I can decide if I want outliers. But if I want to identify the mean and median here, all right, what's going to happen as I move data points? It should show this. And effects of data on changing representations like median and mean. You can also do this with variability. This one's going to actually have different students, I think. And you can compare the variability with each of these and have things like interquartile range. And again, see the impacts on this. So you can actually, the nice thing about computational tools, if you're trying to get to a deeper understanding of what these box and whisker plots are actually saying, and what happens again as different shapes of data are working here, you can actually have a dynamic tool to play with this, and it adjusts with you. Okay. There's a whole host of things in math education related to computational tools that I certainly didn't have when I was teaching high school, middle school, lower secondary mathematics, that we have nowadays. And yet, as you already said, you have things like this, and high-powered laptops, and just wonderful software. It's kind of a renaissance time for math education with computational thinking. The question is the extent to which these ideas are going to be taken up by us as educators. So I want to end with just kind of a comment and suggestion of maybe where to go with this. What are some productive ways to accomplish this? Because I just don't want to just leave you trying to figure out the heavy lifting on your own. So some opportunities. Yeah, try to start small. What are things that you value? What are things that you're interested in? Things that you're familiar with? How are your interests going to be communicated by the choice of a computational tool you want your own students to explore and use? So start with yourself first, and maybe even try to figure out what students are interested in, so you can shift the roles and have students present how the computational tools they're using help solve problems, help them do mathematics. And a nice way to do this is if you're looking for ideas for projects as part of a math course, this would be a great opportunity to bring in kind of inquiry, self-investigation, and see where students go with this. Because the more we get to know what students' expertise is in this area, the more likely we are to kind of bring math education closer to where they might like it a little more than they have in the past. So hopefully this gives you some ideas to work with. And I hope you come away with a more refined understanding of what computational thinking is. So we have time for some questions. Any questions?
Inspiring and stimulating lecture, and now the space for questions is open.
Mm-hmm.
You have enough time?
Could also be a lot to think about. Yeah.
Are there some students in university that are studying only I want to be a computer science? Like, there are some programs if I will.
So that's beginning to happen now. And in fact, just last year at University of Colorado Boulder, we launched our computer science teacher licensure program. Now, a lot of the students that are doing that are coming out of mathematics and are just getting the license on top of that. So, but there are some computer science students who are becoming more interested. The economy changes, and all those jobs that everyone thought was going to be available at Google and Amazon, it's a little different right now. So just as as an option, just to try something, and some people really want to teach. They want to do that. So there are more opportunities in Colorado for that. More and more states are starting to do that. But even without that, even just having some courses in a faculty of education that focus on computer science integration, those can be a helpful start, because more likely than not, it's going to be the math teachers, interestingly, they're going to be doing most of this work. Any other questions? Yeah. Oh, thank you. So you can go to Agent Cubes and Agent Sheets. Basically, that's the website there. If you have other questions for me, there's my email address. The PhET website is also there. You can go there. They have a kind of scroll down. They have a whole section on math if that's what you want to explore. But I would even say look at some of the science applets as well. They actually have some really useful mathematical work that can be done in the context of science. But yeah, Agent Sheets was what we used. Well, hopefully I've given you at least a little clarity on what's coming. In the United States, it took decades, but it's moving very quickly. And because math education hasn't responded as quickly, other educators will take this up. So the question to ask yourselves is, who's going to teach computational thinking? Is it something we're going to leave others to do? And to what extent is computer science even part of the discussion of doing mathematics, given that computer science generally came out of mathematics to begin with? So hopefully it gives you some things to think about. Hopefully it doesn't give you too much to worry about. But thanks for having me here, and enjoy the rest of the conference.
Thank you.